Okay, for this one, let's try doing an example with a little bit of everything. I'll do one with an applied moment in it, a triangular load in it, a distributed load in it, and point loads in it. I ran out of fingers because I'm holding pens. So let's see how we want to construct this. First off, let's assume that I have like this. I have overhang, and then at this end I have I'll have an applied moment of P times L. And here I'll have a distributed load. And here I'll have a triangular distributed load. And over here I'll have some point P. And the maximum of this is P. And each of these are of equal length. L, L, L. Okay, so very quickly, let's find the total load. What is the total load? Let's look at the distributed loads first. We have P times L plus P times L times 1/2 plus P equals 0. Not equals 0, sorry. This is this should be P over L. The maximum is P over L. Yes, the maximum is P over L. That way, when you multiply this, because when you multiply by length, you need to have units of force. This is P over L times L. These cancel, and you're left with 2.5 P. And that is your total load. Okay, now let's call this A, B, C, D. We do moment about B. We get P over L times L over 2. Let's do this way as positive. Minus CYL plus what is this? P over 2 times 4/3 L plus P times 2L plus PL. This PL term is from the applied moment. It doesn't matter where I am in the system, I have to add it if I'm doing sum of moments. I add all applied moments if I'm working with using sum of moments. So let's see what cancels here. This cancels. This is fine. We have one more L that cancels out everywhere. So we have P over 2 minus CY plus 2P over 3 plus 2P plus P equals 0. So these three together are 3.5P plus 2/3 P equals CY. I don't really want to calculate this out. Let's call this 4.2 P equals CY, just to be consistent. And then what does that mean? If notice that our CY here is much larger than our total load, that means that our BY should be negative. Our BY should be holding. So if our thing wants to rotate this way, pretend this thumb here is point C and my thumb here is point B, it wants to rotate this way. So my thumb at point B has to somehow hold it back. It has to pull it back. So we do that. We'll get that By equals negative 1.7p. Okay, now that we have those, let's look at our shear. I'm gonna redraw this. Just so that we have everything on the same page. And let's use our shear. Let me draw the reactions in. 1.7p. When you're doing your reactions, make sure that your arrow and your sign don't cancel each other out. Because there's some people that will point the arrow this way, and then they'll say that this is negative 1.7. Well, a negative 1.7 force for an arrow pointed this way means that it's holding it down. So more information is not always good. More information is actually usually confusing. Imagine if you had lectures where you only had the information that you needed. You never have lectures that only have the information that you needed, which is why lectures are confusing. Yeah, so don't give more information than you have to, otherwise you open yourself up for mistakes. Okay, so we have this. Let's look at our shear diagram. What happens here? We have no shear here. No shear here. No shear here. Our first instance of shear happens here. Here we go up by 1.7p. So I'll call each of these little squares 1, and I'll say we go up to here. And then we go down by 1p over some length L. So all the way over here, we go down by 1p. So let me connect these. This does not go all the way down to the axis. Oh, I forgot to draw one more. One more force here. And over here, oh my god, I'm sorry, I butchered this. While I was going through my little spiel about don't put both of them, I made a mistake here. This here, I normally assume my arrows to be positive, so this should be negative. And that changes everything. So let me erase this and say that we have a downward force here at 1.7p. Normally I'd just remake the video, but I don't really have time today to remake an entire video because of that mistake. I'll keep this diagram though. So we are constant, and then we go down by 1.7p, and then we go down more, right? Go down all the way to here. And then what happens here? Here is like the case we had before, right? It's just reversed a little. So we know that we should start off going down by a lot. As a matter of fact, this will be continuous. It'll be smooth and continuous. And then it'll slowly go to 0. It'll slowly round off. Until we get to here. I messed up this. I'm sorry, guys. I'll tell you where to skip, so you don't have to actually watch through this whole thing where I made mistakes. But from here, I'm running out of battery also. Let me draw this diagram again very quickly. I have a downward reaction of 1.7p, and I have an upward reaction of 4.2p. I have a downward reaction p here. This is p over l. p over l. Okay, if I do this, then let's look at here. My shear, I go down by 1.7p. And then I go, let's call that here. And then I go down by another 1.7. I go down by another 1p over some length here. And then here I go up by 4.2p. Go up. So this is 1.7. So this is negative 2.7. So I'm going to go all the way up to 1.5, right? Because negative 2.7 plus 4.2 is 1.5. So I end up here. And then I go down. I go down by a total of 1/2 p. So I go from here to here. That's going to be parabolic, and it's going to be concave up for the same reason that this thing. So I have the reverse of this in my case here. So that's just something to keep in mind. And then this, we go down by p at the very end. So this is your moment diagram. This is 1.7p, this is negative 2.7p. This is 1.5p, this is 1p, and this is 0. So without even doing any, without any equations, I have been able to draw my shear diagram. Yes, and let's look at our moment diagram. The moment diagram is interesting because we have this applied moment. So we start off at some height p over l. And we stay constant all the way through. I'm sorry, this should be the opposite way. We stay constant all the way through, and then we start decreasing. We start decreasing slowly. So we have a shallow slope, and we start decreasing faster and faster and faster until we get to the average of the area of this is, let's see, this together is 4.4 divided by 2 is 2.2. 2.2p times L. So this thing will end at 2.2p. It'll end at 1.2p. If you don't believe me, you can try calculating what the area of this is, and adding it to negative p over l, or negative pl, and you should get 1.2. I believe I said. I forgot it already. I'll just assume that it's 1.2. You can get the exact numbers later. And I know that it should be steep, and it should be parabolic and getting steeper. And then over here we're adding, so it should be cubic, but you know that it has to end at 0. So you can just draw the last point and then make it extremely steep. And so this is x squared. Give the actual value for this, and say this is cubic. So this is quadratic. Yeah, and then you're pretty much done. Like we just went through this. If you want to calculate these points, just add up these areas. So here you start off with p over l, or negative pl, and then you add this area. To get to this point, you add this area to this area. I'm sorry, see, I keep saying negative. This is positive PL. When you subtract, I have it drawn correctly, but I keep saying the wrong thing because this is positive, this is negative. Yes, that is pretty much it. I know this video looks long, but I'm gonna cut out about 4 minutes of it, I guess. That should make it more manageable.